Okay. Thanks to the organizers for inviting me. I'm really happy to give this talk today. Actually, I will connect to the previous talk on deconfined criticality, but the main part of my talk is actually about a method, a method to extract multiple scaling dimensions from Monte Carlo simulations, which we normally don't do. So here's my outline. So I will motivate this method in terms of exactly the problem we heard about before, deconfined criticality. So I will show a couple of slides on that, but I don't want to spend too much time on these controversies, although we can probably discuss at the end or after. But then, the method I will talk about is basically to, instead of just computing a simple correlation function, we introduce many operators and compute, the whole covariance matrix of those. That's a well-known method in particle physics to extract particle masses from exponentially decaying eigenvalues. But it turns out one can also use them to study power law decays in critical systems. So that's what I will talk about, and I will contrast the exponential versus power law decays with a simple example. And then I will turn to some other equally simple examples, 2D and 3D Ising models, and slightly more complicated case where we have a tricritical point where you do have two relevant symmetric operators, and it's normally not so easy to analyze such things with Monte Carlo simulations. Now the thing is, I developed this method, in some intuitive way. I thought that it should work, but then, I've also tried to prove that it works, but I haven't actually managed. But I think you will see that it works, and I have some sort of maybe outline of a proof, and I hope that maybe some CFT experts here could actually, prove it or help me to prove. But let's see. Okay, towards the end, I will also study another, maybe slightly more complicated example that we are working on right now, and we have some mysteries there. Okay, so the background and I say near future applications here to the deconfined criticality, which we haven't applied this method for yet, but I will argue that it would be very useful. So in this preprint here, which was referred to in the previous talk as well, we have a somehow orthogonal picture to what we just heard in Wei Zhu's talk. Namely, we think everything seems consistent with there being indeed two relevant symmetric fields. So we have to tune two parameters to get to criticality, but that criticality is either a tricritical point, connected to a generic continuous line, or there could be a quantum spin liquid opening in these, quantum spin models that we study. So then you only have criticality here. So S would be the S of 5 symmetric operator that we just heard about, the newly discovered within Bootstrap. Within the fuzzy sphere, although it was actually known in Bootstrap before, if you just don't require there to be only one tuning parameter. So the previous tuning field was just T, which is the one that breaks the SO5 symmetry. Anyway, so in our models that we study with quantum Monte Carlo, we can actually so far not touch the critical point. We go very close to it, so tuning one parameter in our model corresponds to going along a line like that. And we actually get, it seems, so close to that point that even if the transition is first order, we can actually compute the scaling dimensions of the underlying theory. Okay, but we have these two scenarios. We cannot really distinguish between them, but in either case, what we believe is that we see the scaling dimensions of a multi-critical point.
So what's the dashed line here?
Okay, so again, the dashed line is, you see I have two tuning parameters here, right? Corresponding to, in a model, changing two parameters, without changing the symmetry of the model. But if we just take, as we have done in the past, a model with just one tuning parameter, then, these are the scaling fields of the CFT. So if we tune a parameter in our microscopic model, we will change both S and T. And we will move along some curve in this plane. Okay, I will say a little bit more about that. So the models we study are the JQ models, where I didn't even write down the Hamiltonian, but this is the Heisenberg model. It's S dot S on these bonds on the square lattice. The Q2 term is the product of two singlet projectors, which can appear like that or like that. Then we can have Q3, which also there's a horizontal version of. And we go all the way up to Q6. Okay, we also introduce some Z operator, which I will mention in a moment why. So it turns out if we combine these two models, okay, so then we have J and Q2 our parameters. So we change, for example, the ratio of those two. That's what corresponds to going along this line here. Okay, but now if we have, let's say, the JQ2 and JQ3, JQ2 or J and Q3, then again it appears that we come very close to this multi-critical point, so we can actually get some scaling dimensions. And I will show an example where we extract scaling dimensions from these Z2 operators, where singlet projectors are like this. So this is again a 4-spin operator. But now if we go to, for example, JQ6, then the transition becomes very clearly first order. And by the way, I should mention, my co-authors here, Jun Takahashi is actually in the audience here as well. So that's how we can compute, what would be the normal correlation length exponent if you cross here with our model, if you actually happen to cross exactly at the critical point. Okay, so in these, with these large operators, we get very clearly a coexistence state, which means a first order transition. Okay, so here's the table of scaling dimensions that we already saw earlier today. So this is what we get, and I will not talk about all of this. That would be a separate talk. This is just the introduction to a motivation for what I will actually talk about. But let me again mention that the star here meant that Chester and Sood, they took this value from the paper by Adam Nahum, who is also here in the audience, and Chalker et al. And then they used the bootstrap method to compute these other scaling dimensions. I just write 2 star here because it's CFT, so the scaling dimension of the current operator has to be 2. We actually compute it. We have an operator which contains the current operator, and we can actually compute that. So that's one indication that we really are close to a CFT, I think. But then again, as was pointed out, we get results that are pretty close to these other parallel calculations here. Okay, so let me show you how we compute this new T exponent. So we use this Z operator, which again was a 4-spin operator, looking a little bit like a Z. That's why we call it the Z. But then we pack several of them into a square to have the rotational symmetry of the square lattice. And then we compute the correlation function of that operator with itself. And here are results for 2 different models, the JQ2 and JQ3 models, at their transition points, which again are very, very weakly first order. And we all do it in this graph both in a big system as a function of the distance, and as a function of the system size when the distance is L divided by 2. And you see that we get very similar decays of this correlator in all cases. And this is a log-log plot. And you see that it starts to look linear only down here, which means that there are at least 2 strongly contributing power laws in this correlator. This is when we subtract the leading power law, what's left. So in principle, this second one could also be extracted, and we did in the paper, but actually one reason the paper hasn't been published yet is that some of these things were not done, I think, quite correctly. So the leading one is okay, but the way we treated the sub-leading one may not be okay.
But when you subtract, how sensitive it is depends on the numbers you are subtracting.
So you mean the second power law? Well, see, what we did here was we actually fixed the power law because of some reason that was wrong. Let me not even get into it. But this is basically just to show that, well, there may be two power laws there. But let me show you another way how we can get one of these exponents.
Can you explain what is special about the Z operator?
Okay, so in principle we could compute the scaling dimension of the Q operator because we just want the scaling dimension of the operator driving the transition, right? But it turns out the Q operator also contains the order parameter. It's actually sensitive to the VBS order parameter. So the Z operator does not have that. So it should be less complicated to analyze than, well,
How do you see that it does not have the order parameter?
Well, because the Z operator, if you just look at what it does for a columnar state, it would not matter, you know, in what way the columns are arranged. Yeah. So it's more sort of a naive argument that it doesn't actually seem to contain the order parameter. Anyway, here I show the phase diagram that June has extracted for the JQ2, Q6 model. So here it's in terms of Q2, which is 1 minus J, and Q6. And then we have the AFM phase, the NEL phase, and the VBS phase. And the transition is first order on this whole line. So to connect it to these CFT scaling fields, if we go, let's say this is actually the critical point, which it's not quite. So I will argue in a moment that the critical point is a little bit outside here. But anyway, this is this SO5 singlet that would be tuned if we go on the line which has here emergent SO5 symmetry, which we have also confirmed. And then there's some other direction, you know, orthogonal, not necessarily orthogonal in the phase diagram, but in an operator sense. There's the T operator. Okay, so now what June did was doing very careful calculations on this whole phase boundary for different system sizes and extrapolating using a clever trick that he invented to sort of simultaneously get you know, both order parameters where they coexist. And that's the squared, you know, common order parameter as a function of, you know, the distance from this point here. And then a power law can be very nicely fitted there. And that power law should just correspond to the exponent beta, you know, the order parameter as you move away from the critical point. And here the order parameter is, you know, it's breaking SO5. So, you know, the beta exponent, and this would be beta squared because it's, you know, controlled by beta squared because it's the order parameter squared. This is the relation between, you know, exponents and, you know, so this would be the correlation length exponent as you move in there. And this is the scaling dimension of the order parameter, which was in that table before. And this is the value. So this value for beta is quite large, and that's why this is almost quadratic here. Instead of, if you do something like an Ising model, this would be very, very steep here. So that to some extent explains, you know, why systems can be, you know, weakly first order, but still, in some sense, easily be close to critical points. So this also gives, you know, the location of the critical point, which is for negative Q6. And negative Q6 we can actually not reach because we do quantum Monte Carlo simulations, so there are sign problems. And in this case, the sign problem kicks in exactly when Q6 goes below 0. So this is also like an unreachable critical point, similar to the complex CFT scenario, but not as bad, if I may say so, in the sense that we think the critical point still exists in the real world. It's just not accessible with our QMC. So actually right now we are trying to access it with machine learning algorithms and things like that, but that's also
do you think easy. That true critical point has intrinsic sign problem, meaning that no matter?
Yeah, that's actually a very good point. So I think that maybe with some other model we could reach the critical point. But what I also believe is that if this is what we have, if we have this quantum spin liquid here, then we can probably not reach into the quantum spin liquid without the sign problem, because the sign structure of the spin liquid should be something very complex.
But they are models for quantum spin liquid is sign free.
Yeah, but not with this symmetry. Only Ising type. Maybe other ones as well, but I think this is supposed to be a Z2 gapless spin liquid. So, I mean, I cannot guarantee it, but that would at least be that's something I think generally believe that you cannot reach such spin liquids without.
There are some models which at least are written down on paper and were accepted.
Oh, okay. So I guess I should say that with your methods you can.
So I don't know if that's the truth, but at least in principle, these are phases which you could capture with.
Right. Okay. So now you are talking about fermionic versions. Right? Yeah. So I should have said that. We study quantum spin models with one class of methods which have some sign problems. And Faker and others are using fermion determinant methods, which I believe could reach these phases. Yeah, thanks for pointing that out. Anyway, so this is now my way to connect my method that I will talk about to things of interest in this workshop, because this is one way to get that exponent, but I believe that this scaling dimension or this exponent nu s, the delta s here, should be this second power law here, which we cannot really analyze very well with just fitting two power laws. But it would be good to do that, to fit two power laws. And more generally, I showed you the second.
And what about the first power law?
The first power law, I think, is reliable.
Yeah, but which of the exponents does it?
The first power law would actually correspond to delta t. Okay. The second one would correspond to delta s. Okay, so I showed you the table of scaling dimensions. So we can definitely do access some of the CFT operator content, but we would like to do more, because now with the fuzzy sphere and conformal bootstrap and everything, people are also emphasizing the descendants, that we can look at the whole conformal towers and so on, and that's typically not done with quantum Monte Carlo or even classical Monte Carlo. Okay, so the covariance method is again based on a set of operators. So I give you an example here, which I will discuss in a moment, the 2D classical Ising model. So here I define operators on plaquettes with 9 spins. So each dot here means basically an Ising operator. And if I have 3 of them, it means I take a product of 3 of them. And then, in this case, there's only one such operator. But here, you see, I put the dot here. Then I could also put it here, here, or here. So in fact, I add up all those. And that could involve phases or not. Here, I just add them with 1 in front of each of them. So these are all different. Once I symmetrize them, They are different operators, but these all have a Z2 odd symmetry, and these all have Z2 even. So again, if they are connected, it means I take a product. So now, if I would put in cosines here in front, I could make, and in fact I have, but I will not talk about it today. We could also have Lorentz spin not only 0, but 1 and 2 as well.
You mean modular by 4? Right?
So again?
You mean modular by 4, not necessarily by 1, 2, 3.
Yeah, I guess you're right. Yeah. Okay, so now, and then we can compute the covariance matrix, just the correlation function of all these, of this whole set or that whole set. And then my claim is that if I diagonalize that covariance matrix, which of course, the matrix depends on the distance, then I get power laws where the exponents are, different scaling dimensions. Okay, so then does this work? So intuitively it seems like it should, because maybe different R dependencies correspond to some different fluctuation modes, and if I diagonalize the covariance matrix, I should isolate those different modes. It turns out it's not easy to prove, at least easy for me. So maybe it's for somebody here. And I will discuss a little bit later, if I have time, how I have tried to motivate it in the context of CFT. By the way, I mean, there's no reason it has to be limited to CFT either, but maybe CFT is one way to start to proving it, and all examples I will give today would be cases described by CFT.
Yes, you are aware of the work by Martin Lucia and Uli Wolf.
I am. I will cite it in the next slide.
Okay.
Yeah, but it's a little bit different.
Yeah. Okay.
I know it's on the other side of the street, but we do this in radial quantization with Monte Carlo and do get the descendants.
I know, but you do it in a different way, which I will discuss on the next. Yeah. I'm pretty sure. Let's see. So these are the examples I will talk about: 2D, 3D classical Ising, and 2D tricritical Ising. And then later on, well, actually, even first I will discuss this transverse field Ising chain, which is a quantum model, of course. Okay, so this has indeed, as was just pointed out, been used by Lucia and Wolf, and is very commonly used in particle physics to extract energy eigenvalues. So I want to stress that that's not what I'm doing. I'm not extracting the level spectrum, right? But I want to connect that because I think that's something that more people are familiar with. So okay, this is the transverse field Ising model on a chain, and I take periodic boundary conditions, and we have a critical point where these terms are equal. So now we put it on the cylinder, so meaning, well, the Hamiltonian is defined on a ring. So if I do imaginary time, and I go all the way to the ground state, then I have the infinite cylinder. We can also wrap it and do the torus, which is normally what we do in QMC. But anyway, very low temperature. Then we have this, correct conformal geometry to get the level spectrum, right? So now, this is done by Gabe Schum, my student. So he takes 8 operators in this case, and each of these is a spin as Z operator, and this is a product of 3. So these are Z2 odd, and these as well. You see, it's just different ways of taking the product, and symmetrized by reflection. And indeed, as expected, if we go to diagonalize the covariance matrix, we get these eigenvalues that decay exponentially, and in this case we know the velocity is exactly 2. By the way, the font here is annoying because this is V, but it looks like a nu, right? So this is always the problem, nu and V, and sometimes people get confused. Anyway, so these lines here indicate the expected slopes on this log lin plot, and they correspond exactly to the primary, which this is Z2 odd, so the primary scaling dimension is 1/8, and then we have the the descendants. I think this is, Rich, what you referred to that you are doing, and what I think people like Emily here are doing for the fuzzy sphere as well. Okay, but now what are we doing differently? So this exponential you get in the long time limit, right? If we look at shorter times, we actually see power laws. So if we look at short times, the correlation functions, or I should say the eigenvalues, but if you just take one operator and do the correlation function, you will also get one of these. It decays with the scaling dimension as a power law, right? And then we know for long times it's another form. So there's some crossover between these two. And an interesting aspect here is that you see here I wrote delta n. It's some operator with scaling dimension n. But when it crosses over, I wrote it with another delta m here, because they actually don't have to connect to the same scaling dimensions, it turns out. So to really see this crossover, we have only been able to do that in relatively small systems, because these exponential decays are very hard to see in big systems. So here I show an example for L equals 18. So this is using the operators I showed you before, I think a total of 8 of them. And this is the leading eigenvalue as a function of time. And then this red line here is the expected, based on the primary scaling dimension, the expected power law. And the later part, which is shown more clearly here, so this is a log-log plot, this is a log-lin plot. So here you see the exponential decay that I already talked about, that you see eventually. But at least I think here you can, it's not completely clear because the range is not enough, but it looks like there's a little range of that power law decay there. And of course, for very short times, there are scaling corrections. Now let's go to the second eigenvalue. Then the power law decay, and again the line is the expected decay form is more clear, but you also see that it goes to something consistent with the exponential, but now the error bars are already getting big because the power law has already decayed it to a pretty small value. But you see both power law and exponential. And finally the second eigenvalue. But now you see here, in the previous slide, I don't know why it doesn't go back just by one, but here, this was actually the second descendant power law, but here you get the first descendant exponential. In this case, you also get a second version of the second descendant, but and then now that actually also connects to the same one. So why do you get two of them? Well, I will discuss this a bit more later, but it's because the operators we use, which are defined only in space, right? But now we have space-time. So if I want to have a fixed Lorentz spin, the operator has to be space-time symmetric, right? But it's not. And you can see if you just take a space operator, that it's actually a linear combination of L equals 0 and 2. And that you see more clearly if we do, so here, before I showed for one system size as a function of time, longer and longer times. Here are results for when the time, vt, velocity times tau, is fixed at L divided by 2. It's in time, but we fix the time to the system size. And then showing the decay as a function of L. Then you see these very nice power laws, but you get 2 for the descendants. And again, it's because you get the L equals 0 and L equals 2 descendant, which have the same scaling dimensions. Okay. And in this case, no L equals 1 descendant, because they would correspond to, rotating 180 degree and putting a minus sign, which we don't have. Okay, so that was, now I hope it's clear how this differs from the previous method. Although you can say that it's actually exactly the same, but it's like a new application of the covariance method. So, you know, in business, you can patent something which is completely known, but you patent it for the business practice of blah, blah, blah in something. So this is now the new domain of application of covariance matrix. At least I did not find anything before.
In 2D, the exact modular torus is known, right?
Mm-hmm.
So you can use that exact result to unravel what you're doing here?
Maybe. I'm not a CFD expert, but I really like giving this talk here because I hope that people will sort out something.
Exact answer for 2-point functions and so on is written down analytically in terms of Jacobi functions. You can look at the short distance and long distance, and you can see all the wraparound stuff.
You mean I would get this whole dependence that I...
Well, the continuum limit is known exactly. It's called the modular torus.
Right, but so are you claiming that this whole curve would come out from that? Or?
I think so, yes.
Mm-hmm.
Yeah.
I see. That would be interesting to try. Definitely haven't done that. Okay, so now let's show. I mean, so when we do what I just did in the context of CFTs, of course, you have to have the right conformal geometry so that you have the state operator correspondence, so that you can really read the scaling dimensions from the spectrum if we do these long, exponential decays. But this other application of covariance matrices doesn't rely on what geometry you are in. So now we'll just look at the 2D classical Ising model, which is just, of course, the same as the model I just showed, but in periodic L by L lattices. So that it's not like this long imaginary time dimension. It's just two equal space dimensions. And these, again, are the operators I use. So first to show here, now I take a large lattice, L equals 256, and I look at distances much less than L. And first I just show you the correlation of the individual operators, so no covariance, just looking at that one times itself or that one times itself and so on. And you see that eventually they all decay with the leading scaling dimension, that of the primary. Except, in the case of the antisymmetric one, you have strong boundary effects, because even though these distances are pretty small, since the decay is so slow, there's contribution from, let's say, the mirror image of the second operator as well. So you get these well-known enhancements of correlations because of boundary effects. But anyway, before that kicks in, it works pretty well. And in the symmetric case, the decay is faster, so you don't really see a lot of those boundary enhancements. But now, in principle, these decays here, they should contain the whole tower of scaling dimensions. But it's, again, very hard to analyze this kind of data if you want to fit to 2 or more power laws, right? So what do we get if we diagonalize the covariance matrix? Well, in this column here, I just used 2 operators, and I think I used, in this case, the 1 and 4, and in this case, I forget. Anyway, just 2 of them. And in the second column, I use 4 of them. In the paper, I also show 6 of them, but it looks pretty similar to 4. So if we just use 2, then of course we have only 2 eigenvalues, but they reproduce very well the expected scaling dimensions, where the leading one is the primary, and the second one is the L equals 2. In this case, we don't mix in L equals 2, it's just L equals 0, because these have full symmetry on the lattice. So it's the second descendant that we see there. When I go to 4 operators, in principle I have 4 eigenvalues, but the 4th one actually is, the values are just 0 within statistical errors. You see that the overall magnitude goes down as I go to higher eigenvalues. But we kind of see the second descendant. So here the decay is 1 over r to the 10, which is a pretty fast decay to study with Monte Carlo. Okay, so I should point out something here. So when you diagonalize the matrix, most software will just give you the eigenvalues increasing or decreasing order. And this is how I colored them here. But you can see in this case that it looks like the coloring is not correct, in the sense that, you know, here the green dots seem to continue as the blue ones, and here the blue ones sort of seem to continue as green ones. So there's a sort of swapping of the order of the eigenvalues that happens along the way there. And if I look at the eigenvectors corresponding to these eigenvalues, you indeed see that, you know, something crazy happens, you know, in the region where they are very close to each other. But then finally, you know, so these are the components of the 4 eigenvectors. The solid ones is for, you know, one of the eigenvalues, the open ones for the other. So you see that eventually they converge to some well-defined distance-independent eigenvectors. Okay, and then to show you that it also works, and this may be important for people like Facker, if you are restricted to small system sizes, you would normally look at the correlations as a function of you know, half the maximum, half the size of the system. So that also works here. There's a little bit of a mystery to me here. So this 4th eigenvalue, in this case, I also resolved the 4th one, but it doesn't decay as the 3rd descendant would. It still has the same decay as that one. And that could be because it has not reached the asymptotic behavior, or maybe there should be 2 of them. I'm actually not really sure. But anyway, the 3 first ones are okay. And this is to show that if you look at the eigenvectors, either, you know, for a small system or a big system, but at the same distance, the eigenvectors actually look exactly the same. Modulus statistical errors. Okay, let me go to the 3D Ising model. So here I use similar operators, but now I just took 4 of them. But, you know, of course, the 3D Ising model, if I want the full space-time symmetry, I should also make the operators 3-dimensional. But I didn't do that here. And one reason for that was that I wanted to sort of mimic what we would typically do in a quantum system, where we define our operators in space. It would be hard to, at least for me, I think, to define some operators that are space-time symmetric. So then, if I have such planar operators, I can look at the correlations within a plane, which I will refer to as space-like. But I can also look at them, you know, line them up on the same spatial region, well, same position in a layer, but look at them in different layers. And this is what you would do in, and as I already did in the 1D case, in a quantum system as a function of time. But the decay power should be the same in this case. Well, always for CFT, I guess. So here I show, you know, time-like correlations. They actually seem to behave a little bit better, but in the paper there's also space-like ones, and they look the same. So this is again the known primary scaling dimension, and this is basically taken from the most recent CFT bootstrap paper. So it's the, you see the primary, but then again now the first descendant should be doubled, because again these operators don't have fixed L, they mix L equals 0 and 2. But here it's interesting, if I look at the Z2 even one, I get something which is actually consistent with scaling dimension 3, so the decay, I mean, it's not super convincing maybe, but you should expect here, because the energy momentum tensor has scaling L equals 2, and I should have an L equals 2 here, and the scaling dimension should be 3. So maybe it's reproduced here. I think I will try to do that a little bit better. Okay, now let's go to a more challenging case. The Blume-Capel model, which also is referred to often as the diluted Ising model, because you have up and down spins, but you also have empty sites that you can think of as vacancies, or you can just think of them as spin zero. So that's the Ising term, and that's sort of the chemical potential for the actual spins. So by changing lambda, you have more or less vacancies. Okay, this is just some name I gave to this term, E and then delta F. So F is not the free energy here, it's just my name for that term. So this model has been studied a lot, and the reason why it's interesting is that it has a tricritical point. So I took this phase diagram from this paper here. So you see here is the tricritical point at temperature about 0.61 and lambda around 1.97. And then above that, the transition is first order, and then it's continuous below, and this is the regular Ising critical line, and it ends at that tricritical point. And the scaling dimensions, of course, are known from CFT. And from this paper, they determined this location of the tricritical point very accurately, so I just took that value. So then the question is, can we, so now we have two relevant primaries here. So can I extract those with this covariance method without having to do fitting to two power laws? So now I define some operator here. Again, red dots mean the Ising operators, the sigmas. This blue square means sigma squared, and blue open squared actually means 1 minus sigma squared. For some reason I thought that would be nicer to use for these, but it doesn't really matter. Okay, so then I compute the correlations of all those 6 by 6 correlation functions. But first I just, out of those, 6 by 6 matrix, I just pick two operators. So that one can do, post simulation, we can pick any of these correlations to construct smaller covariance matrices. So this is what it looks like if I just look at, and this is actually the operators O1 and O2. So if I look at just O1 times O1, I get these correlations, and O2 times O2, this one. So they decay with the same leading power law, again, compared with what it should be. And again, there are some boundary effects. So if I diagonalize, then here you can almost, on this scale, you cannot really see what's beyond this leading power law. But here you do get the second one. Even if the amplitude is very small, you get it quite nicely. And if you just do it with these two operators, which, those two operators correspond exactly to this E and F here. So if you look at the eigenvectors, one of the eigenvectors will actually, if you analyze it correctly, will correspond to actually going from the critical point into the first order line or into the continuous line, which can be useful, when you analyze these critical points and locate them to actually get these directions. So that I also checked, against known results. So if I do the whole 6 by 6, I get these eigenvalues. And again, here the system is big. It's L equals 256, and I look at it as a function of R up to not very large distances. So these are the two primary scaling dimensions. And then there's another primary that I see here, which has scaling dimension 3, and I believe that's the pink ones. And then the other ones are descendants. And of course, the last one here, I don't claim that I can extract it very well, but at least it's consistent. And then one can also do it as a function of L divided by 2 and basically get similar results. There's a little bit question about, the black and the pink, which one actually has scaling dimension 3 and which one has 3.2, because there's a descendant with 3.2. So it's actually not so easy to see, but okay, so one final example will be, if you look at this tricritical model, if we sit exactly at this tricritical point, then of course we get those scaling dimensions. And if we go into the Ising line here, then we should see the regular Ising exponents, scaling dimensions. But then if we go close to the tricritical point, but still on the Ising line, then initially, as a function of distance or system size or whatever, the behavior will actually be controlled by the tricritical point, right? And then eventually it will cross over to the regular Ising. So that's pretty interesting to look at here as well. So here I just list some points at which it was done. So one, at the tricritical point, and then you see these are, close to that point. And then there's one point which is very far away, where there's no lambda at all, but that's still not the normalizing model because you still have the vacancies there. But anyway, it's clearly on the Ising line. So this shows the eigenvalues, the first eigenvalue, second, third, and fourth for all these points. So the red points correspond to the tricritical point. Same as I showed you before, this is the tricritical primary expected decay, and the second expected, third, and fourth. And now you see if I go to the furthest one away from the tricritical point, this one here, that's the blue open ones. So here you see the Ising, normalizing decay here as well. Here it gets a little bit difficult, but at least it's consistent. But then you see crossover. So if you are super close, of course, you don't really even see the crossover. So this again, connects back to what I told you about the JQ models, where we are close to the critical point, but not quite there, or multicritical, and this is also multicritical. But in that case, I was slightly on the first order line. Now I'm slightly on the critical line. But you see, if I just go to small distances, I pretty well get the tricritical behaviors. But here, for this point, you can start to see the crossovers here. But now, very interestingly, if you look at, so these are the primaries actually, the tricritical primaries, and in the Ising case, one is a descendant. But if you look at the one that at tricriticality are irrelevant and descendants, then you see that the eigenvalues are actually super stable. You get tricritical behavior for all these points except the one that is extremely far from the tricritical point. So here we could see the crossovers in these descendant irrelevant scaling dimensions. We don't even see the crossover. They still look tricritical even though the primaries have already crossed over. So I don't know if that's some known thing or not. Okay, so I think I don't have a lot of time to show how this can work, which is in some sense good because, as I said, I'm not claiming I can really prove it. But let me just spend a couple of minutes outlining what I have done, which is more not really a proof that it works, but establishing some conditions that are needed for it to work. Okay, so if I look at CFT operators and I just take one multiplet, so this would be the primary and then it's all its descendants, and these would be the scaling dimensions. So here I also fix the Lorentz spin. So if I look at L equals 0, I would only get every second one. So that's what I want to do. Now we can look at the covariance matrix. So these operators are not orthogonal to each other in the sense of correlation functions because they belong to the same multiplet. And thanks to Ami Katz for teaching me that. So the decay should mix the two scaling dimensions. Okay, you can think of this as a vector as well. So the covariance matrix would be this vector thing here. So now I'm asking what is required for, if I diagonalize this matrix to get this disentangling of the scaling dimensions that from the numerics seem pretty clear that we get. Okay, so then I do some unitary, or I guess just orthogonal in this case, transformation of these operators. So that I call the transformed operators Q tilde. But note that this transformation will have to depend on the distance between these operators. They don't just, it cannot just depend on the operator itself, as far as I can tell. So if I just look at a finite set of them, and eventually I can take the set going to the whole set here, but if I just look at a finite one, which maybe is more practical to work with, then you know, this U transformation has some matrix element UNI, operator N, and then it mixes all these different original operators here. So then, okay, so if I write down you know, the transformed correlation function, which eventually I will see what is required to make it diagonal, but now you can just think of it as some transformation. Well, this is the correlation function from up here, CKP, so I can just put that in. And then I want to pull out, you know, since now I have all these power laws coming from there, there's nothing wrong with just pulling out something that eventually I want to get. So I pull this R to delta I plus delta J out, and then because of this relationship between the primary and descendants, I get something like that. And now what I want to do, and this is, you know, where I need to assume something, or I think this is something required for this whole thing to work, that, okay, so this U, this transformation depends on R, but how about if I can cancel that R dependence and just get some V which does not depend on distance anymore. So then, you know, if that R dependence is attached in this way, then I just get something like that. And now I just have to diagonalize one thing, one matrix, and then I get the full R dependence of the form required. So once it's diagonalized, delta I equals delta J. Okay, so this is what I don't know if it somehow is true for a CFT or not, but I think this is actually what's required. But what did this give me? This has nothing to do with the lattice still, because this was just to create a set of CFT operators that are orthogonal, even though they are in the same multiplet. Now there's one more.
Sorry, can I ask, why do you need this? I mean, your lattice operator is an infinite sum over various CFT operators.
That's right.
For a fixed, let's say, set of lattice parameters, it's a set of fixed coefficients.
That's right.
So you don't need to perform a R-dependent transformation.
Well, but otherwise I cannot prove that it works, right?
Well, I mean, it's just, I mean, any lattice will have an infinite.
Yeah, okay, so that's the second. So maybe you can ask the question after I.
This is a known problem. There's a solution with the exponential, and you have to take this into account.
I know for the exponential case, there is a solution. So Lucia and Wolf, they prove it.
Does that exponential thing carry over to this? I think.
Exactly. So I looked at that, and I don't see it carrying over in a way that I can do, but maybe you can do. But let me. I mean, I think it must be true, right? I just don't know enough about CFT to do it. But but let's see.
I would say it's just a property of effective theory. It's not really.
Okay, let me just go through this very quickly. So if I now take lattice operators, okay, so my lattice operators, now I can expand them. And of course, you know, the lattice operators act on the lattice and the continuum operators in the continuum. So I realize that this cannot be mathematically true, but in some coarse-grained effective sense, I can expand my lattice operators in those operators that I had made orthogonal in the previous page. Okay, then I can just look at the covariance matrix of those. And if I use the previous result, I can replace that correlation function, which now is diagonal. And then I can just work from there. And eventually, you see that there's a very easy way to diagonalize the covariance matrix once I use that result. but there's one subtlety here which actually is probably expected. So this goes up to infinity here. You know, I have an infinite number of continuum operators. So if this just went up to n, and I have n operators in my covariance matrix, then there's a very simple solution for these w's, which themselves are quite complicated. But for the w's, they just have to be Kronecker deltas. But of course, it's not completely true. So, but these decay very quickly for higher k. So it will just be some small modification of that. Right. Yeah, I'm pretty much wrapping up now. Okay, so I also had some results for this Wess-Zumino-Witten kind of spin chain, where it also seems to work. We get non-scaling dimensions, but we had one mystery here. Before I showed the transverse field Ising model, we get the same behavior in space and time. Here it seems like we get known scaling dimensions in time, but in space, but it's like we miss one in space. I get a primary and its descendant, but in space with only two operators, I get the primary and one of the marginal operators. So we are not quite sure why we somehow seem to miss one, but we need to do more operators and so on. Okay, so this is actually the end of my talk, so thank you very much.
The questions or remarks?
Maybe I have a couple of questions. So first I was curious which algorithm you used to simulate the tricritical Blume-Capel? So just control.
Well, I used for the spins, not vacancy ones, I used the cluster algorithm. And then I just did Metropolis for changing spins to vacancies. I just recently saw Hasenbusch has a paper claiming that he has some cluster algorithm for the whole thing, but he didn't present any details. I don't know. But anyway, it was good enough, but it would be better to have a better algorithm, I think.
Another question was, if you repeat this calculation of the eigenvalues, picking up only the lattice operators which are already in the Hamiltonian, then you will be able to figure out what's the right combination that gives you picks up only one relevant perturbation. Then you get the scaling axis.
Well, so that's what I did in the case of the Blume-Capel model, right? This first example here, where I did only two, I did operators O1 and O2, right, and they correspond exactly to these two. I see. So then I went kind of fast, but that's how the eigenvectors actually give me the relevant direction.
Right. So then you have that's interesting information.
Yes, I think this would actually be very useful also when people, for people who study gas-liquid transitions, right? Where, there are also Ising transitions, but in the Ising model by symmetry we know how to separate the directions, but in the gas-liquid you don't know.
Right, exactly. Yeah. So, you can choose one direction to pick up only one observation or not. Yeah.
Sorry, maybe I missed it, but did you explain what you do with the covariance method on the lattice? I mean, you diagonalize the correlations at each R, or what?
Yes, exactly. So you just compute all these operator correlations. So for each distance you get a matrix, which we call the covariance matrix, and then you diagonalize it individually for each R, and then plot the eigenvalues as a function of R. So it's actually very easy, and again, very similar to what people do, but people have done it in the past to extract exponential decays.
So for the DQCP, previously, the paper that had the earlier version, I think you were not using this method.
Exactly. So this came after that, but now, of course, we want to apply it to that. And I've been meaning to get started on that for some time, but there are lots of things going on. But definitely, the next step now is to, in addition to the Z operator that I told you to take some other few similar operators and see if we can from the covariance matrix get delta t and delta s. And hopefully, if we can get descendants as well, with the correct separation, that will be a strong evidence for a CFT, right? Yep.
Perhaps I don't understand this, but you're on a torus rather than a radial quantization.
That's right.
So doesn't the wraparound on the torus give you breaking of conformal symmetry and some crazy?
Yeah. So this is what I don't understand. Right? I mean, when you extract the eigenvalues of the spectrum, you need to be in the correct conformal geometry. And here I have shown that you don't need that. So there is something in this method which is not relying on that.
Because you are in 1 plus 1.
Well, but also in 2, I also did the 3D. I did also this one, right?
No, in 1 plus 1 it is radial quantization.
Right.
In 1 plus 2 it is not.
Exactly. So I did 1 plus 1 in radial, but then I also did the square L by L, which is not. Right?
But then you're breaking conformal invariance by the finite volume effects, and with power law dependence, those are not small.
Exactly. So, but still, it works.
But here you don't check R dependence, right? You fix R, then the scaling symmetry tells you the exponent.
Yeah, but
no. I mean, of course, I mean,
It could still work. I mean, it's more confusing how it works if L equals 2 over 2, but if R is small, it would still.
Yeah, exactly. So when R is small, it should not matter.
your diagonalization is in Fourier space.
Of course, it's not going to work.
No, my diagonalization is not
Of course, it's not going to work on the torus.
Torus is diagonalized in Fourier.
Of course, it's not going to work for exponential case on the torus. It's not going to work. I mean, you should talk to Andreas when he gets here later today. He did these calculations on the torus. You will extract those energies, which are not scaling dimensions.
Exactly, you get energies on a finite volume rather than scaling dimensions.
But Anders is not doing this long torus, right? He's doing cubic torus, and he's just looking at L over 2 separation. So just by scaling symmetry, you'll pick up the scaling dimension.
I mean, I think I'm just not using the state operator correspondence. I mean, and exactly why it works, I don't know, but you can see that it does work.
Well, this is analogous to Lucher's attempt to get partial waves out of a torus. He has to do an incredible transformation to get to the partial waves from the Fourier space of a finite torus.
Right.
And I would think you would have the same problem here in spades.
I mean, initially I definitely thought that, but then it's not the case.
The equation on the third line of your slide, that is not going to work in 3D.
Right. It's not an equation.
No, you mean this one?
That's a Hamiltonian in the box.
Yeah, exactly. No, this also only works in radial quantization.
Right. So there must be some.
But this seems to work, irrespective of how my system is wrapped.
That's the consequence of scaling symmetry.
Well, I mean, it even works in R equals L divided by 2. And maybe you remember when I talked to initially, I also thought that it didn't work, but it does.
There is some obscure paper which tries to do a sort of Lucher untangling of the Fourier modes to conformal modes, but it's very complicated.
Right, and maybe even more complicated.
That's really just scaling symmetry, right? There's only one scale and the scale invariant, and that gives you pretty exponents.
I just don't understand why we have to invent a new language where there exists already a well-established language of renormalization group, scaling operators, and all that there is goes with it. Why can't we just stick to the usual language, which has been around since
what unusual language did I use?
That we should, you are inventing here some method, covariance method, and you are not connecting it to first principles.
Well, I'm connecting it to this crossover.
But why should you not connect it to first principles?
Well, I'm not a CFT expert. Okay?
It's not a CFT. It's Ken Wilson was not a CFT person. He was a renormalization. He invented a renormalization group. That's been around for 50 years. Why are we not?
Well, okay, so why I'm doing this is simply to get the scaling dimensions, and I would love to be able to derive it, but sorry if I'm too stupid to do that. I haven't done that, but I think the method is useful.
Well, get yourself some experts, at BU that have plenty of CFT.
Yeah. Well, you know, I definitely try to talk to them.
I think it's correct. I just don't think it's R-dependent.
It's definitely not.
So you think I should just not tell you if I haven't proven every detail? That
Seems to be very preliminary results.
yeah. Well, is that wrong to present preliminary results? I mean, that's a pretty weird workshop if you cannot discuss things that are not completely settled.
As an effective theory, it's fine.
Anyway, further questions before we go forward?
One more question? Yes. Sorry, I didn't understand what you said about why you like the Z operator in the JQ model. Is it because you don't want to take a superposition of this and this?
Well, it's more because, okay, I have to take some operator which has all the symmetries of the Hamiltonian and perturb me away from the critical point. And the natural one would be the J or Q operators. Now, if I do their correlation function, they actually also contain the order parameter, the VBS order parameter. They will have.
That's the part I didn't understand because it's symmetric, right? It can't have
well, okay, the thing is at the deconfined critical point, you also have the plaquette state, you know, which becomes sort of degenerate with the columnar state. So this plaquette operator actually also picks up the VBS order parameter. Yeah, I mean, I can show you some clear evidence of that.
So here, technical questions. So here you show the eigenvalue as a function of the distance.
Yeah.
Say for the leading eigenvalue, how about the eigenvector change as a function of the?
Yeah, I mean, change as a function of. Oh, yeah, that I actually did not show here. To be honest, I didn't analyze it in detail, but yeah, that would be interesting to do. Of course, I have the eigenvectors, I just haven't, you know, it's preliminary, right? So, I mean, there's a preprint out, but I haven't done everything.
When you go to larger distances, the transformation becomes R-independent?
Well, the eigenvectors definitely become R-independent. Yeah. Well, I mean, I did check it at the critical point, yeah. I mean, I showed you here too. At some point I had a slide showing that. Like, okay, here I told you in some cases, not always, but sometimes the eigenvalues sort of cross each other, so then there's some weirdness. But eventually, you know, these are coefficients of the eigenvectors, and they go pretty flat. And then I showed you this one, which was even for fixed, okay, this is for fixed distance, but in two different system sizes. And I mean, as a function of distance, they do converge.
Okay, so the G is eigenvector, right?
That's right.
Okay.
Yeah. So here there are 3 eigenvectors, and these are the components of the eigenvectors. I have six operators, so there are 6 coefficients. Yep.
So you mentioned Martin Hasenbusch for the Blume-Capel. I mean, I don't know whether he did it this way, but you could probably treat the spin 1 as a pair of 2 spins 1/2, which you know how to do, and then you have to project out one of the double-counted 0 states by something you do in the last time series.
Yeah. Oh, but this is even classical, but maybe classically one can do something like that. Yeah, it's possible. Yeah. I mean, it was pretty efficient anyway, but yeah.
I don't. I had a question about why you can't get closer to the critical point, given that you're already so close. So
you mean in the DQCP?
Yeah. Since you think you're very close, and it's just that you have to move a little bit in the direction of the T operator. If you do that only using Q6, you get a sign problem.
Yeah.
But there should be many operators which will only give you the T and no S. Do they all have a sign problem? Have you looked at?
Yeah, well, you know, I think it's hard to take a lattice operator which contains only T or S. So, you know, we have
why is that hard? If you're just type linear combinations, well, like where you'll remove S.
I mean, that's literally what you're doing.
Exactly, yeah. So that we haven't done yet, but eventually, if I get this going for the JQ model, we should be able to do that. Yeah. But then I do fear that you know, if we go on well, anyway, we go to make it more continuous will probably give us a sign problem. But I'm not sure. I mean, it seems that we should be able to get a little closer or maybe even all the way there.
What is the intuition? Why would it?
Yeah, why would it give you a sign problem for all of?
Well, I mean, my intuition is you know, more or less, if we have this scenario, which is the one I think is more likely, then, you know, this VBS and AFM phase in at least in the sign problem free region, it has a very simple sign structure, and that's why we can even do QMC, right? So now I think everybody agrees, and maybe Subir can say what he thinks, but I think the sign structure of this gapless spin liquid is must be something very complicated. You cannot just write down a Marshall type sign rule. So then I think we can at least not do QMC of, you know, the type that we are doing, real space type path integrals in that case, but maybe we would be able to reach the tricritical point. That seems plausible.
Maybe it's a good moment to is there one more urgent?
I mean, since you mentioned, so there is a work by Federico Becker and collaborators of a very specific wave function for the QSL.
Yeah, which I think would maybe can be done with fermion QMC, but not with the kind we are doing, I think. But maybe with a fermionic model, one would actually be able to do that. Yeah, maybe Fakar can help with that.
Maybe it's a good moment to conclude.